So having understood sufficiently about phase diagrams, okay, we need to extend our understanding further, okay, simply because what is lacking in phase diagrams, what information is lacking? Phase diagrams tell us about existing phases. Basically, when you apply equilibrium conditions at all the stages of phase change or whatever, okay, whether you are heating or cooling, if you do it at a very slow pace, okay, infinitesimally small pace, speed, okay, then you get the phases the way they are portrayed in your phase diagrams. But in the practical scenarios, is it possible? Can you take 1 month time or 1 week time or several days of time just for heat treating a material just to get the equilibrium phase? No, it is practically or economically not viable. It's not only that. It's not that always equilibrium phases are desirable. Okay, for instance, we know the martensite, right, which is not a equilibrium phase, which we call non-equilibrium phase or metastable phase, which is desirable phase rather than ferrite in some places where we want the high hardness for the material. So that is why we always in practical situations the heating or cooling takes place at relatively faster pace, that means a little away from the equilibrium state. So the correspondingly the resultant microstructures, resultant phases may deviate from the equilibrium phases. One of the classical example for that is getting this martensite when you go at a very fast cooling rate, okay, of the steels, okay. So that is why, but to study the martensite, unfortunately in phase diagrams you cannot accommodate it, because phase diagram is basically for equilibrium phases. So we need other diagrams like this time temperature transformation, which we call TTT diagram, which has got its other names also as mentioned in the slide, basically to address this time factor, okay, so that you can also discuss about martensite and other such phases, or what happens if I go at a particular cooling rate. So all these things can be understood, which has more practical relevance, okay, in the workshop, okay, for an engineer, for a metallurgist, okay, or for a material scientist to understand in the practical scenario when you go at a very faster rate what phases I get, okay, or what kind of mechanical properties I may get as I change the cooling rate and so on, right? Which is not possible, this information is not available in the phase diagrams, right, because phase diagrams are basically to understand the theory theoretically, okay, for it is more for for the people who are looking for equilibrium phases existing for different materials and so on, okay, right. So let us talk about time temperature transformation diagrams. As I said, they also being called as isothermal transformation diagrams or C curve. Of course, the names are derived simply because of their own inherent nature of the way we cool them or heat them and so on. I will, when I show one of the diagram, I think you better understand. So let us quickly see, this is one example diagram of TTT diagram for a eutectoid steel. What is eutectoid steel? What is the carbon percentage? You all know, it is carbon of 8% of carbon. Sorry, 0.8% of carbon, right? That is a eutectic mixture, right? So eutectoid steel means a steel having carbon of 0.8% of carbon, right? Now, unfortunately, these diagrams, TTT diagrams, are not, if you give iron carbon alloy system, I will not be having just one diagram, okay? You will have different diagrams for different compositions. If you have carbon percentage 0.2%, you will have a different diagram. If you have carbon percentage 0.4%, you will have different diagram. For example, this particular diagram belongs to the carbon percentage of 0.8%, that is nothing but eutectoid steel. What is so special about eutectoid steel? It is having completely one phase, that is 100% perlite. You don't have ferrite, which you will have if you have less than 0.8% of carbon, that is hypereutectide, or you have cementite also along with perlite. If you have the right side of this eutectide, isn't it? That is beyond carbon percentage of 0.6, 0.8 percentage, right? So now we are taking only a special case where it's only eutectoid steel. That means entirely you have only perlite. And if you see the diagram, okay, you have essentially two lines. One is red color, the other one is green color. And if you see the x-axis, time, okay, and y-axis it is temperature. So essentially what happens with time, okay, at a particular temperature, that's what we are trying to read using this particular diagram. So assume you are at say 500 degrees Celsius here, and your material is at this temperature, and you are just trying to observe what is happening with time, that is horizontally, okay. So what happens as you move here, so at this particular point, okay, something is happening. That is what is red line. The red line shows the initiation of the formation of perlite, okay, perlite starting point, okay, and from here up to here what you have, it's only gamma, that is austenite, right? So you have austenite. As you at this particular temperature you keep this particular material, after some time this particular eutectoid steel will start converting to perlite, and if you come to here, it is partly austenite. You see here it is partly austenite and partly perlite, okay. And if you keep going right side, there is a green line which indicates the completion of the complete conversion of austenite into perlite, okay. So here perlite formation started, it ended here, okay. That means the total austenite is being converted to perlite by the time you come here, okay. Now as you go on along this line, nothing is happening, so your perlite retains, okay, until the room temperature, okay, or whatever. Of course you once you reach to this side of the line, and then you can cool it down at whatever the pace you want, and you will only be having your perlite, okay, with you, right? So so ideally what is happening now, okay, what we are trying to understand here, at a constant temperature, okay, how the transformation is taking place is what we are trying to understand with time, right? At what after what time it starts, after what time it will end, the perlite formation is what we are trying to understand. So that is why, since we are observing things at a constant temperature, we call them isothermal transformation curve, okay, IT curve, or in other words, what is the other name? C curve, okay, because the curve typically looks like C, alphabet C, okay, English alphabet C. So we have three names. One is time temperature transformation, isn't it? Because at a particular with time and at a particular temperature, how the transformation is happening, that is what you are trying to observe. Or it's also called isothermal transformation. We are seeing at a particular temperature how the transformation is taking place, or simply C curve, okay. So any of the name can be used, okay. So what is the use of this, okay? The use of TTT diagrams is to understand, for example, you take any steel, okay, to any temperature, okay. Say for example this is austenite, right? You take some in this particular case eutectoid steel you have taken here, and practically what is the use of this diagram is, what happens if I bring this suddenly to a particular temperature from this high temperature austenitic temperature and keep it at that particular temperature constantly for some time. So because essentially I want to affect the way it is being converted from austenite to some other phases, okay, and that varies depending on at what temperature I am trying to transform that austenite to some other phase, okay, phase. So if I say choose 550 degrees or above and keep this austenite at this particular temperature for some time, so what happens, slowly perlite starts formation and perlite end formation, that means it totally converts to perlite, okay. Rather if I choose a temperature below 550 degrees Celsius for this particular eutectoid steel, okay, for example at 400 degrees here, and then keep it at this particular temperature constantly. With time, slowly what happens, instead of perlite, there is something called bainite. Okay, so bainite starts forming. Okay, and after some time, all this path here, it is actually converting slowly from austenite to bainite, and here the process completes. So you have total bainite here. After that, with time, nothing will happen. So you have complete bainite with you. Okay, so what is bainite? That we will discuss in the subsequent slide. Basically, bainite is also like perlite, consisting of your ferrite and cementite, but mostly this ferrite is consisting of more of dislocations. Okay, that means the ferrite that you find in bainite is actually the harder than the ferrite that you see in perlite. So that much of detailed knowledge at this point of time may not be required for you, but at least you understand that based on the temperature you will be having different phases. Okay, it may be perlite or it may be bainite. Okay, if it is above 550 degrees Celsius for a particular alloy, that is in this case a tetroid steel, it will be perlite. Below 550 degrees Celsius, it will be bainite. Is there any other phase? Suppose we always want martensite. We have been discussing so much that we want to convert your austenite to martensite directly instead of ferrite. Yeah, that can be addressed here. You see, you take it from austenite and suddenly take it somewhere here. Okay, this red line, like below this red line, and keep it for some temperature. Okay, so slowly then it will be converted to martensite. Okay, so there is a critical temperature below which if you bring it and keep it for some time, you actually see that austenite is being converted to martensite. Okay, however, you can have you can affect the microstructure based on your requirement. You can have some fine perlite sometimes where you want. Okay, you can have coarse perlite, you can have fine upper bainite, you have lower bainite. Okay, you can have martensite. Each one have their own, each one of this phase having their own properties, like the with respect to hardness, tensile strength, and so on. So typically, if you see at the top, you have coarse perlite, which is slightly softer. If you go to finer perlite below here, if you want fine perlite, it will be harder. Similarly, bainite, it will be little harder because you have more dislocations, and if you come to martensite, it will be much more harder. Okay, you already know that. And what is the crystal structure of martensite? It is BCT. Okay, body center tetragonal. Okay, right. So you now know for this particular alloy, if you want martensite, what you have to do? Take it to a temperature above 750 or so, and suddenly bring it to a temperature below 200 degrees Celsius and keep it for some time. So slowly everything will be converted to martensite plus, of course, based on the temperature. If it is below this line, it will be completely martensite, and if you keep it somewhere here, it will be martensite plus austenite. Okay, it is called unstable austenite. Okay, in this particular case. Yeah, so let us move on to some other type of diagram, that is continuous cooling transformation. So what is the difference between this and the TTT diagram? In TTT diagram, basically we are keeping a particular sample at a constant temperature and trying to see with time how the phases are changing. But in CCT diagram, this is more relevant for practical purposes, simply because practically very difficult to keep samples at constant temperature. So in this particular case, what we do, we simply these diagrams will give you if I go at a particular cooling rate, okay, what happens. Okay, so for example, if you go at 5 degrees Celsius per second, you get perlite. If you go at 40 degrees Celsius per second, you get something else. And if you go at even faster rate, 140 degrees Celsius per second, this cooling rate, what you end up with? Martensite. So with respect to different cooling rates, what is the kind of phase you are going to get is what you are you are going to read from this diagrams called continuous cooling transformation. Okay, this is again for a particular material, it will be different. For example, what you are seeing on the screen is for 1080 steel, So and you can see the dotted lines comparison, that is nothing but a comparison with the TTT diagram.